Okay, we have this problem on the board from the MIT Integration Bee 2015. This is problem number 4 from the qualifying exam. I thought this was unusual because the question just asked this part, the integral of secant x. And that's a known integral, a standard integral, so you wouldn't expect that on the test. And then when I looked at the answer, they gave this part, inverse hyperbolic secant cosine x. So my interpretation of the problem is rather than try to integrate and get this, our job is to show that this integral equals this, and that's what I'm going to try to do. So first we're just going to use the standard result for the integral of secant, which is going to be ln absolute value secant x plus tangent x plus c. Now check the rules of the MIT Integration Bee. They don't require absolute value signs. They don't require the c. So let's rewrite this, and we want ln, and just use parentheses, secant x tan x. We want this to equal hyperbolic secant of cosine x. And so because this is an inverse function, what I can do is let's rewrite this on the other side. So we'll write hyperbolic secant of ln secant x plus tangent x equals cosine x. So if I can manipulate this left-hand expression and get this to be equal to cosine x, then we can come back at the end and say that this expression is true. And what I want to do, just so I don't keep rewriting this ln expression, let's call this piece y. Then by doing that, we can just work with hyperbolic secant of y. Now the hyperbolic secant is just going to be 1 over the hyperbolic cosine, cosh y. But then we have a definition of this that we can use. Cosh is just e to the y plus e to the minus y over 2, and this whole thing's over 1. But then we can flip this into the numerator. Next, what I want to do is I want to find some expression for our e to the y and e to the negative y. So let's look at e to the y first. So e to the y is going to be the same thing as, we'll bring back our, in terms of x, our ln expression. So this is going to be the same thing as e to the ln secant x plus tan x. But then because we have e to a natural log, these cancel and we'll just end up with secant x plus tangent x. But by knowing e to the y, we know that e to the negative y is just the reciprocal of that, so that's going to be 1 over secant x plus tan x. And actually, I think before I continue, I should do some more cleaning up on our e to the y expression. So what I want to do is let's change this in terms of sines and cosines. So our secant x here is going to be 1 over cosine x, and our tan x is going to be sine x over cosine x. But then we've got the same denominator here, so we can add these together and have 1 plus sine x over cosine x. So again, that's going to be this piece right here. But then this piece is just going to be the reciprocal of that, so it's actually going to be cosine x over 1 plus sine x for our e to the negative y. That's going to be this piece. So then rewriting this whole thing in terms of sine and cosine, we have this here on the left. But you can see again, we want to get a common denominator here in order to try to put these two pieces together. So on this one, we're going to multiply top and bottom by a 1 plus sine. Sorry, that's kind of small. And then here we'll multiply top and bottom by cosine x. Then from here, what I can do is bring this up into the numerator, and then we'll multiply out this denominator here. Okay, so now multiplying out the denominator, we have this expression, but we can see we're going to have some more simplification because this piece right here is just 1. Sine squared plus cosine squared is 1. So then what we can do is just add this over to this other one, and we're going to have a 2 here. This is gone. I'm just going to clean this up, factor out a 2 from the denominator, so we get a 2 and a 2 here. So when we write this, we'll have 2 cosine x times 1 plus sine x over 2 times 1 plus sine x. And that's going to give us cancellation here and cancellation here. And then we're just left with cosine of x. Then let's just go back to validate what we did. We started basically here. We wanted to evaluate secant of y, where y is ln secant of tan x, which is just the integral, the known integral of secant x. And then we worked through all these steps to show that this is actually just equal to cosine, and that's what we wanted to show right here. And so we're done.